Good morning, everyone. Hope we're all doing well today. Again, someone send me a message. Let me know everything's coming through loud and clear. Thank you. All right, so 4 more classes to go. Week 14, day 2. Going to continue on today with talking more about photons of light, and which is going to lead into a discussion of different models of the atom, which we're going to talk about on Friday and Monday. So I want to, today though is mostly about talking more about this nature of light where it's a wave, but its energy is absorbed in chunks called photons. So we're going to do a bit more problems like that. And most of your problems today, we'll continue talking kind of just about photons, and I'll do a few examples of those as well. So the main idea for today that I want to get into is thinking about how this idea that Einstein proposed of the photon model for light can seems contradictory to what we know about light. And in particular, before spring break, you guys all did and performed an experiment showing that light was definitely a wave phenomena. That it's this thing that's spread out in space. If you shine it through a double slit aperture, it diffracts and interferes and gives you an interference pattern of bright and dark fringes on the screen. And all of this is characteristic, the way we know that something's a wave. So I want to talk about how this, how the photon model of light kind of goes together with this. So on the surface of things, you would think that, all right, light has, the energy of light is absorbed in these chunks. So perhaps this means that light is actually made of particles. And originally in the development of optics, the main debate over whether light was a wave or a particle was a thing that happened very early on. And eventually the double slit experiment proved that light was a wave. But here we see something different, where we're seeing that, for instance, imagine if we do we take this double slit experiment, and where our viewing screen is, we put a detector, maybe a piece of camera film or something that records where light hits. The contradictory thing about the photon model is that if you had a really, really dim light source, and really dim, so you only have a few photons going through, few photons worth of energy going through and hitting the screen, it's not just that the energy is absorbed in chunks, but that it's absorbed in localized positions as well. So if you set up the double slit experiment and just shined a few photons through, you would see things like this, where those chunks of energy are absorbed at particular locations on the film and expose the film. However, if you kind of let the light source there exposing the film for a really long time, what you'll see is an effect like this. More and more photons will come through, more light will hit the screen, more photons will be absorbed, and they'll be absorbed kind of in, wherever they hit. And if you keep this experiment going even longer, all of a sudden you get, you measure more photons that they hit the screen, and eventually, if you let this go on long enough, eventually that double slit pattern of bright and dark fringes will start to form. Which, if you think about it, is really kind of, it's weird, but also super cool. So the energy in the light, even though the energy from the light wave is absorbed in these localized spots and these discrete chunks, each of those little chunks of energy carry with it all of the wave properties. So somehow light is both a wave, but its energy is also absorbed kind of as if it was a particle, something localized in space, which is contradictory and weird, but we have to kind of go with the experimental facts here. So even if we use a really dim light source, where individual photons can be measured and detected one at a time, eventually the wave properties of light, if we measure this for long enough, emerge. So it's not that these two models seem contradictory, but whatever it is, whatever light really is, it has aspects of both particles and waves. It diffracts, but its energy is also absorbed in these discrete chunks at discrete locations. So these individual quanta of energy still carry all of the wave properties. So these two models can kind of be used together, is one of the things this means. It also means that nature is a lot weirder than we initially expected, which as a scientist is something you really want to see, because what's the point of doing science if nature is boring? You can also see this whole effect if you look at photographs. So for instance, if you take photographs in dimmer light, things come out grainier, meaning like have this grainy effect where you have parts of the film exposed, other parts not. And this is because in really dim light, you're absorbing individual photons, but if you expose the film for long enough, eventually the whole picture will form. So regardless of the experiment we're doing or what we're trying to measure, the photon model of light and also the wave model of light, both are kind of active at the same time. So just because light is being absorbed, the energy in light is absorbed in these chunks called photons, doesn't mean we can ignore the wave properties. So from here, I like to kind of work through a lot of the problems on the next set here are problems where you're given different properties of a light source, like the power or the wavelength, and they're hitting something, and you want to, ideally, they're asking for some quantity that you can find by relating it to the number of photons that are absorbed. And this is a very good example of such a problem. So here we have a 1 watt light source, and it's a light source with a wavelength of 550 nanometers, which is yellow-greenish. And it's hitting a silicon solar cell, so like a solar panel. And we're exciting, essentially, in the solar panel, something similar to the photoelectric effect happens. We're not knocking electrons out into space, into free space, but we're knocking them out of the valence shells so they're free to conduct. And that allows us to generate a current to produce electricity. So this problem doesn't give us very much information. It gives us the power and the wavelength, and we want to know what's the maximum possible current, electric current, this light can produce in this block of silicon. So let me show you kind of how we can go through that. So first of all, remember here that the power is telling you how many joules per second are being delivered, so it's energy per second. So this 1 watt light source delivers 1 joule per second to this piece of silicon. And we're going to make the wrong but simplifying assumption that all of this energy is absorbed by electrons. Obviously, nothing is 100% efficient in real life, and silicon solar cells are not close, but for the sake of the problem, just to show you, we're going to assume that. So we have 1 joule per second hitting the silicon solar cell. In order to find the key fact here is, in these problems, you're going to have to use the total number, you're going to have to use the number of photons you have. So let me try here to, so the key thing, we want to find electric current. So to get the electric current, what we're really going to need is the number of electrons per second that are created. We have the number of electrons per second, we can multiply by the charge of an electron to get the current in amps. So this is really what we need, the number of electrons. If we assume that each electron that's knocked loose from its valence shell is going to be knocked loose by 1 photon, the number of electrons is going to be equal to the number of photons we have. And we're going to assume that they're all absorbed. So our goal is to use this information to get the number of photons. So that's kind of the main work. So here, the power gives us energy per second. And from what we know from last class, we know how much energy there is in one photon. So we can kind of combine these ideas to get the energy of one photon and then figure out how many photons we must have. So first things first, let's use the wavelength and the speed of light c, 3 × 10⁸, to get the frequency. I'm going to let you guys check these numbers on your own time, but these are all formulas you've used before and theory from earlier in the class. So frequency is speed of the wave divided by the wavelength, 5.5 × 10⁻14 hertz. Once we have that frequency, we can use our energy of a photon equation from Monday, Planck's equation, to get the energy in joules in one photon. So for one photon, this is how much energy it has, 3.6 × 10⁻19 joules. 4 photons for this frequency. Now we just need to know how many photons total per second do we need to get this amount of energy per second. So some unit analysis could get us that. So we kind of think if we have 3.61 × 10⁻19 joules per photon, and we need 1 joule per second, we can divide the two numbers to get the units of photons per second. And so what we have here, by a small order of magnitude estimate problem, we have 2.77 × 10⁸18 photons per second that hit this silicon solar cell with a 1 watt light source at this 550 nanometer wavelength. So taking this number, our assumption is going to be this is how many electrons we have per second, because each photon is absorbed by 1 electron. So number of photons becomes number of electrons, multiplied by the charge of the electron. That's this guy. And that will give us the current in coulombs per second, or amps. So in the end, this is the maximum current we could possibly get is 0.44 amps. In reality, not every photon is going to be absorbed by an electron. Not every electron is going to remain free to conduct. It'll lose it. It'll hit a nucleus somewhere, lose its energy, heat up the silicon lattice. So this is really like a maximum possible current. So a lot of your problems today are going to focus on this type of kind of unit analysis. Are there any questions on the process? All right, good. Again, I think, luckily, I think this material is a bit more straightforward again, and it's a nice break to have after going through all the magnetism stuff online. So this is hopefully a little bit more straightforward. So let's see here. So this is going to be an example problem for you guys to work through. So here, I guess the setup of the problem here is that we have laser removal of birthmarks happening here. And they're being removed by using a laser that is 585 nanometers in wavelength. And pulses are absorbed by the birthmark, which destroys them. And we're given some properties of the laser pulse. We know how long the pulses last in milliseconds, and we know how much energy they contain. So here we want the power and how many photons. So it's similar to our last problem. I'm going to let you guys work through this, and when you guys get an answer for the power, send it to me in the group chat. Please, if you can, send it to everyone so people can check answers. And then once you have the number of photons, do the same. I'll be quiet for a few minutes and then check in. And if you have questions, feel free to ask me them now. Otherwise, I will shut up and let you guys work for a bit. Okay, any questions about that? Just need more time to work? Okay, as you guys work, I'm just going to, for the sake of the recording, I'm going to put up the answer for the power. So the power of the light wave goes back to last semester. We need the energy delivered per unit time. Seven joules divided by 1.5 milliseconds. I'm just going to round a bit here, around 4,600 watts approximately. All right, so as for the number of photons, Brittany, it should be a few orders of magnitude lower. I check your frequency. What frequency did you get? Might be best, everyone. Let's see, what frequencies do people have? Remember here for the second part, we need the energy in one photon, which is going to be Planck's constant times the frequency. So we need to find the frequency first. Order of magnitude here, I think you may 585 nanometers. Remember, that's 10 to the minus 9 meters. So I think you're missing I think you have a unit issue in that answer. So Sabrina, yes, 5.112 times 10 to the 14. That's what I get. I think everyone, if you're not getting that, try to go back and check your units on nanometers. I remember speed of light is 3 times 10 to the 8th meters per second. So here we have to work in SI units. given that we're given energy in joules. All right, so that, I agree with that frequency, 5.13 times 10 to the 14. So what do we get for the energy of one photon then? Remember, you have to use H in Planck's constant in SI units, which I'll send you in the chat. So I am getting as well 3.4 times 10 to the minus 19. So if you're getting something lower, sometimes that might be using H in electron volt units rather than SI units. So this is the energy of one photon. So instead of writing out all of those constants with my mouse here, I'm going to write out the final energy here. So this is the energy of one photon. So I'm going to write this as 3.4 times 10 to the minus 19 joules per photon. So now we need to find the total number of photons. Call that N. It's going to be the total energy, E, divided by the energy of one photon. So it's going to be 7 joules divided by this number. So Bree, your power of 10 is, it should be positive. We should have a lot of photons rather than very few. So I think you may have reversed the fraction here. So total energy divided by energy of one photon. Yep. Okay. So, yep. So everyone is now coming in agreeing on 2 times 10 to the 19. Okay. It's worth, so just like as thinking about how you check your answers and know whether you're in the right ballpark or not, if you have a bright light source like this, you are going to have a lot of photons. Remember, a photon is the amount of light that's really being given off by like one electron transitioning between an energy level or two. That's what the energy in one photon is, on that order of magnitude. So if you have a laser light source that you can see, or a light bulb or something, you have a lot of photons. 10 to the 14, 10 to the 19, 10 to the 20. Those are the answers that are reasonable for number of photons for a problem like this. Okay, so this is then 2 problems now that kind of work with, a lot of it is rearranging units like this along with Planck's equation. Does anyone have any other questions? These are 2 good examples of the problems you'll get today in the homework. Okay, if not, then let's, I'm just going to spend a few minutes here, the remainder of class, okay, introducing what we're going to talk about uh, next, next class. So kind of connected to this material. So here, remember what I said at the beginning of the class, that if we see a diffraction pattern like we saw in lab, that it's showing that we have wave phenomena for light. So that this is proof that light has wave properties. It diffracts, it interferes. We can produce an interference pattern in a double slit experiment. Now, the really crazy thing is that, so for instance, you can take a beam of electrons. So maybe we have our photoelectric effect source producing all these free electrons maybe, and then we accelerate them through a capacitor and we shoot them at a screen that picks up the electrons. If we put a double slit aperture in the way, you would think that electrons being particles would not produce a double slit pattern. They should just kind of go through and hit the other side without making a bright and dark fringe pattern. However, that is not the case. Nature is weirder than that. So even if you try to use you try to do a double slit experiment with electrons, particles of matter, if the double slits are small enough in width, and you let enough electrons hit the screen, go through, hit the screen, and then hit the detector on the other side, you will produce, at least effectively, a double slit pattern. More electrons will hit in certain spots where the screen is brighter. Less electrons will hit in darker spots. And statistically, if you let enough electrons go through, they'll hit in this bright and dark fringe pattern, which, as we found, is characteristic of a wave. Is really quite a strange phenomenon, that something that we know is definitely localized particle of matter, a localized chunk of stuff, still for some reason acts as if it's spread out in space, going through both slits, diffracting and interfering with each other, with itself, and then that determines where the electron hits on the other side. It's really quite strange, very non-intuitive, and I can't say that, I don't think anyone can really say that they fully understand why this is the case. However, it's an experimental fact that small subatomic particles of matter have wave properties, just like light has some properties of particles. The energy in light is absorbed in discrete locations and chunks. Particles, which are localized in space at a discrete location, can diffract and interfere given the right conditions. So just like light has properties of both particles and waves, subatomic particles also have properties of both particles and waves. And the guy that, if you've taken a chemistry course, you probably talked about this guy, Louis deBroglie, who is the person who kind of made this connection. So that just like light has properties of particles, particles of matter should have some kind of wave-like nature as well, that it should be kind of reciprocal. And so what he said, what deBroglie postulated, is that electrons have some wave property. They have an effective wavelength. As for what the hell is actually waving, that is much harder to say. But deBroglie postulated and then went on to show that this effective wavelength is given by Planck's constant divided by whatever the momentum is. The faster the object is moving, it's given by its velocity v, the smaller the wavelength of the particle. Bigger the mass of the object, the smaller the particle, or the smaller the wavelength, effective wavelength. And it's this effective wavelength that then determines, if you do this double slit experiment with a beam of electrons hitting the slits and then measuring them on the other side, it's this effective wavelength that will determine the bright and dark fringes you see. So this is, we're not going to do problems with this today, or not many, other than maybe to, in the homework set, to compute the effective wavelength for different particles, different, this works for electrons as well as any other subatomic particle. The math is straightforward. The intuition as to why this is happening is something that, you know, if you guys figure it out, please let me know. And I'll tell you how you can go and apply for your Nobel Prize. But it is an experimental fact. And we have to, and it helps us explain a lot of things, particularly about how the atom works. And that's mainly what we're going to use it for, just to finish up this class. So this effective wavelength, just for sake and problems, it's named after Louis de Broglie. It's called the de Broglie wavelength. And as a picture of what is happening here, this thing I'm talking about, if you have a source of electrons out in air, out in free space, that you could fire at a double slit, even though they are particles, the electrons that go through these slits will somehow diffract and interfere with each other, which affects the statistics and the probability of where they hit the screen, giving you an effective diffraction pattern. So there's some kind of wave associated with each electron that comes out. How it's associated, what is actually waving, we don't know, but the experimental fact is there. And this experimental fact that electrons have this associated wave nature determines, in particular, in how the atom works, in particular, why there are energy levels inside of an atom. So why electrons cannot take just any energy, and why there are particular energy levels, and thus why, for instance, hydrogen gas has particular lines of absorption and emission. So it determines a lot we know about the spectroscopy and chemistry of atomic gases. And we're going to talk about that on Friday. But I'm not going to do much here. So the thing I want to highlight, though, is that this is a very kind of ridiculous concept, if you think about it. Like, so what de Broglie is really saying is basically any type of particle or big conglomeration of matter effectively acts like a wave. So what he's saying in some cartoonish picture is that, like, if we had a wall with 2 holes in it, and we kicked a soccer ball at that wall, that soccer ball is effectively a wave that is extended out in space, and that soccer ball, the wave associated with that soccer ball, will go and travel through both of those slits at the same time, diffract outward, interfere, the 2 waves will interfere, which will determine on the other side of this wall where the soccer ball will hit. And this is a completely patently ridiculous concept. A soccer ball is clearly not a wave. It goes through one or the other, and if you hit somewhere in the middle, it won't go through the slits at all. So what is happening here? Why do we see this effect at the subatomic level, but not at the level of soccer balls or real life? And theoretically, this is the case, but these effective wavelengths that de Broglie postulated are exceptionally small. And that's the reason we don't see this effect in daily life. So if you actually kind of go through and calculate what the wavelength of the effective wavelength of this soccer ball would be, about 1/2 of a kilogram. If you get a good kick going, kick it 60 miles per hour, which is probably exceptionally fast, but let's just take some numbers here. And so that's like 26 meters per second. So if you compute this effective wavelength for the soccer ball, that effective wavelength is around 10 to the minus 35 meters, which is exceptionally small, patently ridiculously small. If you want to think about size scales here, 10 to the minus 10 meters is about the width of an atom. 10 to the minus 15 meters is about the width of a nucleus. So we are, about 15 orders of magnitude smaller than a nucleus, which means that in order to see this effect with a soccer ball, we would need to kick it at a double slit aperture where the slits were spaced apart by around half, or 15, the space between the slits needs to be 15 orders of magnitude closer than the width of a nucleus, which is completely patently impossible. So this is why we don't see this effect on the scales of everyday life, because the effective wavelengths associated with objects at scales of everyday life are so absurdly small. However, if you did the same computation for an electron moving from an electron beam gun at a double slit source, these wavelengths are significantly bigger, enough that you can actually see this effect and build a double slit aperture that has the right spacing. And the main difference is the mass of an electron is so much smaller, which makes the effective wavelength so much bigger, which allows us to see this effect. So we'll never see this effect on the scales of everyday life, but with subatomic particles, we will. So here, 10 to the 15, here I said in the slide, 10 to the 20, we would need to be something much, much smaller than the radius of a hydrogen nucleus to even see this effect. That being said, it's still important on the subatomic scale. So all these effects kind of wash out and disappear on the scale of everyday life. But on the subatomic scale, they are still important. And this plays into our development on the models of the atom, which, if you remember maybe from high school chemistry or your chemistry at college, our models of the atom kind of developed over time. And just as a review, our original primitive view of the atom, and by primitive I mean near the end of the 19th century, was, at that point we knew electrons existed and that they had negative charge, but protons in the nucleus hadn't been discovered yet. So our model for the atom really looked like this: all these negative charge particles in this soup of positive charge. But then once positive charge was discovered, we didn't really know about the nucleus yet, but we might postulate that there's like particles of positive charge kind of all around like this. Of course, we know that now this is not true. J.J. Thomson, not knowing the atom, having discovered the electron but not the proton, developed what he called the plum pudding model of the atom, meaning that there was just this soup or gel of positive charge with electrons stuck in it. It proved to be obviously incorrect once protons in the nucleus was discovered. If you ever wanted to know, you may have heard this term before if you studied chemistry. If you ever wanted to know what plum pudding actually was, it's a Victorian British dish. It's like a boiled cake, essentially, with raisins in it. So here the model is like the cake is the nebulous positive charge and the raisins are the electrons. There's actually no plums involved at all. It's just the Victorian era word for raisin was plum, which is a fact that I expected I suspect you did not plan to learn in your physics class, but it's a cool one nonetheless. So once the way we discovered positive charge and that it must be very concentrated was by scattering alpha particles that are helium nuclei, 2 protons and 2 neutrons together, off of gold films. The fact that most of them traveled through the film without scattering off in different directions led Ernest Rutherford to think that all of that positive charge must be condensed in a very, very small area in the center of the atom, which he called the nucleus, and then the negative charges were around the outside. So this kind of leads into the more the picture of the atom, kind of like a solar system. It's called the planetary model of the atom. That the electrons orbit around the nucleus, kind of like planets orbit the sun. So this was a bit later in 1913. But there's one subtle problem with this model. And it comes from what we learned a few weeks ago. In that if an electron is orbiting around the nucleus, kind of like shown here in our little picture, little cartoon, it's accelerating and it has an electric field that moves along with it. So what that results in is a changing electric field in space. And so through Faraday's law and Maxwell's law, this moving electron will create this changing electric field, which will then create a changing magnetic field, and so on and so forth, and it should produce a light wave. And in some sense, that's good because it explains why gases might, like hydrogen, give off light. However, so in principle, that's good. But the problem is it would mean that depending on how fast the electron's rotating around the nucleus or orbiting the nucleus, it could give off all possible frequencies. And we know that that is not the case. If you've looked at the light emission from hydrogen gases in one of your chemistry labs, you'll know that it only gives off specific frequencies or colors of light. So this model, just the planetary model, would predict it could give off, in theory, any frequency. So there's something missing there. But there's also another problem, and a much bigger one. And it comes from conservation of energy. If our electron orbits the nucleus like a planet orbiting the sun, and the electron must give off light, but that light carries away energy. As we know, photons have energy. So that means that as the electron gives off energy, it's going to eventually spiral around in a smaller and smaller circular orbit until it eventually crashes into the nucleus, and then everything is done. It means that atoms as we know them wouldn't exist, and we wouldn't be here to talk about them. So clearly something is wrong with the model of the atom as we knew it at the beginning of the 20th century. So what we are going to do in the remainder of the class is figure out how this idea of the electron having an effective wavelength fixes this problem. So the last part of the class here was really more of a history lecture than anything, but it's worth knowing all this info before we talk about the science. So we're going to try to go forward from here and fix this problem in the next few classes. The last thing I'll say here is, you may be wondering, well, if you're a good scientist, you say, well, maybe this is the case. Maybe the electrons and all of the atoms in the world are slowly spiraling in closer and closer to the nucleus, and billions of years from now, we will all fall apart and matter will collapse, and then the universe will end. If you're a good scientist and probably a very, very pessimistic person, you might say that. However, we're not going to do in this class, it's a very advanced calculation, but you can calculate how quickly the electron should theoretically crash into the nucleus if the planetary model was correct. And that amount of time, the average amount of time it should take to collapse, is 10 to the minus 11 seconds. So that would be 1/1000th of a nanosecond. So if the planetary model was true, where electrons were just simply orbiting around the nucleus, then hydrogen atoms and matter would have existed for less than a nanosecond before they collapsed into something else, and the periodic table wouldn't exist. We wouldn't be here to exist to talk about it. So this is a big problem in science at that time, where a model broke down. And we need to extend the model, add in a new idea to fix it. And that's going to be the idea that the electron in the atom has an effective wavelength. And we'll see how that will fix this problem when we come back on Friday. So that's the end of our lecture for today. Thank you all for listening, and I'll talk to you soon.